A multilayer perceptron is a neural network where the relationship between input and output are nonlinear. It has an input layer, an output layer, and one or more hidden layers. Here in this figure, this blue one is the input layer, and this is the hidden layer, this black ones, and this green is the output layer. Here we will talk about the backpropagation learning algorithm in multilayer perceptron in details. When we give the input and observe the output, and if we have a training data set, then the training data set will tell us what is the error for a neural network unit for a particular input, so that this error is reduced by updating the weight. But for a neural network, the training data set will give observable values only at output nodes. That is, suppose this is a neural network. Okay, this is our input layer. These are hidden layers. These are output layer. And we have connections between them. Then for every nodes here, that is nodes at the output layer, we get the value of the errors from the training dataset directly. And we can minimize the error by updating the weight here. But this weight updation is only work for output layer, because we doesn't know the value of the nodes for a training example for any nodes here or here. So what we are doing is that the error we are finding at the output layer, we are going back to the previous layer and propagate the error and estimate the error at the previous layer. We say that the error here is partially because of the error computed here. So the blame of the error in output layer is partially dependent upon the error in the previous layer, which is dependent upon the error in previous layer. So we will take the error for an output layer and backpropagate it to the other nodes from which it takes the input. If we look at the weight of these nodes, the contribution of error is higher when the weight is more. In neural network, input signal computed in forward way. But when we calculate the error, it propagates the backwards way. That is, we find error at output layer, and the error here backpropagate the previous layer, and based on the notional error, we update weight for previous layer. So we have the output layer and we find the values of output and error, and we update the weights here, and then from the notional error here we update the weight here, and then again we update the weight here. So the error is propagate in backwards way. That is why this algorithm is called backpropagation. Now let's get into the mechanism. By minimizing error, what we actually mean is minimizing the cost function. Let x is the output from the network and y is the actual output. Then cost function c equal to x minus y square for a training example. We know that cost function is the function of weights and biases of the network. We are trying to minimize the cost function with respect to weight and biases. That is, we will find out the weight and bias that will minimize the cost function for each training example, and we will update that in our network. For that, we will have to find out partial derivative of cost function with respect to weight and partial derivative of cost function with respect to bias. That is, finding of partial derivative of cost function is the heart of backpropagation algorithm. Now let's start with the simplest neural network with 4 neuron and 4 layer. That is, each layer has a single neuron. And we have weights W1, W2 and W3. And we have bias B1, B2, B3. And then our cost function C equal our cost function C is the function of W1, W2, W3, B1, B2, B3. Then, and we have to minimize the cost function with respect to each of these variables. Now let's focus on the last 2 neuron. In this last neuron where we get the output, and this is the previous neuron of that one. We name it as AL1 and AL-1, and we will name it as AL. And suppose we have an output Y, that is actual output, and our network gives output of AL. Then our cost function C naught equal to AL minus Y square, and we know that AL equal to sigma of WL AL minus 1 plus BL. Now let's give some notations to reduce the complexity of this situation. Let's give ZL equal to WL AL minus 1 plus BL. Then we get AL equal to sigma of ZL minus sigma of ZL. That is, we have WL AL minus 1 BL together form ZL, and from ZL we get AL, and from AL and Y we get our cost function. This is the diagram that relates our variables. From this diagram, if we have a change in our weight, it is clear that there will be a change in ZL, and again there will be a change in our activation energy that makes a change in cost function. That is, a small change in our weight can cause a change in cost function. Now if we zoom out a bit, then it is clear that for AL minus 1 also there is a ZL minus 1, and that forms using some WL minus 1, AL minus 2 and BL minus 1. So this weight WL minus 1 can have a influence in our cost function. That is, the weight WL minus 1 has a change. If WL minus 1 has a change, then ZL minus 1 has a change, and it propagates through the neuron, and we get that our cost function is also has a change. The ratio of this change of cost function with respect to the change in weight is the partial derivative dou C by dou WL. Now let's calculate this partial derivative of the cost function with respect to weight WL. So the partial derivative of dou C with respect to weight equal to partial derivative of ZL with respect to WL into partial derivative of AL with respect to ZL into partial derivative of C naught with respect to AL. That is, ratio of change in cost function with respect to weight is the product of ratio of change of variables between cost function and weight WL in the diagram. Now let's calculate each of the terms. First, let's calculate cost function with respect to AL, and we get this dou C naught by dou AL equal to 2 into AL minus Y, and dou AL by dou ZL equal to derivative of sigma function, and we get dou ZL by dou WL equal to AL minus 1 from the equation. Then we get cost function with respect to weight L, that is dou C naught by dou WL equal to 2 into AL minus Y into sigma dash ZL into AL minus 1. So we have an AL minus Y term in the partial derivative of cost function with respect to weight. That is, even if the change is very small, it's still significant in the cost function. We also have an AL minus 1 term in the partial derivative of cost function with respect to weight. That implies the change in weight with respect to cost function is also highly influenced by how strong previous neuron is. This is the cost function of one training example with respect to weight. Now we have to take all the element in the training data set, and we get dou C by dou WL equal to summation of k equal to 1 to n dou Ck by dou WL, and 1 by n because we are taking the average of all the training example. That is, partial derivative of cost function with respect to weight L is the average of partial derivative of cost function for each training example. Now let's calculate partial derivative with respect to bias. Let del C naught by del BL be the term, then del C naught by del BL equal to del ZL by del BL into del AL by del ZL, del C naught by del AL, similar to how we calculate del C naught by del WL, we get is equal to 1 into sigma dash of ZL into 2 into AL minus Y. That is 2 into sigma dash ZL AL minus Y. Then similar to weight, here also we are taking average of all the training example. Then we get del C by del BL equal to 1 by n sigma k equal to 1 to n dou Ck by dou BL. From this partial derivative of partial derivative of cost function with respect to weight and bias, it is clear that our cost function is highly sensitive about the difference between actual value and network given value, and for a training example, and activation at the previous node and sigma function. From the partial derivative of cost function with respect to weight L, we can update the weight WL using gradient descent, as WL is updated as WL minus eta into dou C by dou WL, where eta is the chosen learning rate. Similarly, we can update bias BL as BL minus 1 eta dash dou C by dou BL for a chosen learning rate eta dash. Now we are trying to understand what will happen to this partial derivative with respect to weight and partial derivative with respect to bias when we have a neural network of multiple neurons. So consider a neural network and its last two layers, that is Lth layer and L-1th layer, and denote AJL as the activation of jth neuron in Lth layer, and AKL-1 is the activation of kth neuron in L-1th layer. Then similar to one neuron case, we get our cost function C naught as a sum of squares of difference in output required and network output. That is C naught equal to sigma j equal to 1 to n n 1 to nl aj l minus yj whole square. Suppose we have nl neurons in this layer. And to find zj of l, we denote wjk is the weight of signal between AKL-1 and AJL. Then we get ZJL equal to WJ0L A0L minus 1 plus WJ1L A1L minus 1 plus etc. plus WJNL minus 1 ANL minus 1 L minus 1 plus BJL. Then activation at jth neuron, AJL equal to sigma of Zj of L. Then partial derivative of cost function with respect to weight is essentially the same as the previous case, that is one neuron per layer case. That is dou C naught by dou WJK of L, that is cost function with respect to weight JKL equal to dou ZJL dou WJKL dou AJL dou ZJL dou C naught by dou AJL. So sensitivity of weight for a cost function is essentially the same as previous case. Now let's find out the each term in the partial derivative of cost function C naught with respect to WJKL. So first let's find out the partial derivative of ZJL with respect to WJKL. So from the equation of ZJL we get it is AKL minus 1. Then from AJL's equation we get partial derivative of AJL with respect to ZJL equal to derivative of sigma and partial derivative of C naught with respect to AJL equal to sigma j equal to 1 to NL 2 into AJL minus YJ. Then we get the cost function with respect to cost function partial derivative of cost function with respect to weight JKL equal to 2 into sigma j equal to 1 to NL AJL minus YJ AKL minus 1 sigma dash ZJ. And when we take average of all training data set, we get the cost function dou C by the WJKL. Now we are trying to find partial derivative of cost function with respect to a weight of a neuron that's not connecting to output layer. So for that, let us consider our previous example of 4 neuron. neural network. So for that we have a diagram. So from this diagram we can calculate partial derivative of C naught with respect to WL minus 1. That is equal to dou C naught by dou AL into dou AL by dou ZL into dou ZL by dou AL minus 1 dou into dou ZL minus 1 divided by dou AL minus 1 into dou ZL minus 1 divided by dou WL minus 1. Similarly, we could find dou C naught with respect to dou BL n minus 1. That is partial derivative of cost function with respect to the bias BL minus 1. So, in this way, we can find partial derivative of cost function with respect to any bias and with respect to any weight in this neural network. So basically what we are doing is traveling backwards from the output layer to find the weight and bias we need, and from the diagram we get the partial derivative that we need. For any arbitrary neural network, we can create a diagram that will be insanely big, similar to what we draw for our simple neural network. From that diagram and the equations we have for each neuron, we can find partial derivative of cost function with respect to any bias or with respect to any weight. And then we can update the weight and bias in order to minimize the cost function.
So we'll be showing you the implementation of backpropagation from scratch, explaining the steps as we go about it. The only package we'll need for our implementation is the NumPy numerical processing library. First, let's define the constructor to our neural network class. The constructor requires two arguments, layers and alpha. Layers represents the architecture of the network. For example, when we say that our layers is 3, 2, 1, it means that our first input layer has 3 nodes, our hidden layer has 2 nodes, and our final output layer has 1 node. Alpha specifies the learning rate of our network. Now we move on to the next part. So we need to define our weights. To define the weights, we start looping over the number of layers in the network except the last block, which is visible here. The final block is for the special case where the input layer needs a bias term but the output does not. So if the ith layer has m nodes and the I plus 1th layer has n nodes, then the weight matrix W is a m plus 1 cross n plus 1 matrix. This is including the bias term. So an example is visible here. Then we normalize this weight by dividing it over the square root of number of layers. This is the code for the last layer where the input requires a bias term but the output doesn't. Hence, there is no plus 1 visible here. Now, we can define our activation function, which is sigmoid in this case. So, we can see this as it returns the value 1 divided by 1 plus e raised to minus x. Now we go on to define the derivative of the sigmoid function, which we'll be using during backward pass. We have defined this function as sigmoid deriv, and it returns the value x into 1 minus x. Next, we go to the function fit. Fit requires two parameters, x and y, and another two optional parameters, that is epochs and display update. The first parameter x is the training data, and the second parameter y is the label for each entry in x. We can then specify the number of epochs we want to train our network for, and finally, the display update allows us to see the training process at specific intervals. Then we insert a column of ones after the last column of x. This is to allow us to train the basis term along with the weights. For each epoch, we loop over each data point, which is visible here. Then we compute the backpropagation phase and update the weight matrix, which is as shown here. We shall be defining the function fitPartial next. This part deals with the printing of the training update in specific intervals. Now we move on to the function fitPartial. The fitPartial function requires two parameters, x and y. We also have a list called A. A is responsible for storing output activations for each layer as x moves forward. Then we loop for each layer, and the net input to the layer is obtained by taking the dot product between the activation and the weight matrix, which I have highlighted here. Once this output is applied to a sigmoid activation function, we get the net output. This net output is then appended into A. Hence, the last addition of A is the output of the last layer of a neural network. Now we move to backward pass. The first step is to calculate the difference between the predicted and actual label. The change we make in our weights is due to delta. So that is, delta will be used to update our weight matrices, which will be multiplied by the learning rate. The first entry in delta list is the error of our output layer multiplied by derivative of the sigmoid for the output value. As we know, the delta for the final layer, we can now go backwards using a loop. The delta for any current layer is equal to the delta of the previous layer dotted with the weight matrix of the first layer. Then we multiply it with the derivative of the sigmoid function of the activation for the layer. This value is then stored in D. This process is repeated until we reach the first layer. Now we go on to the step of weight updating. To perform our weight update phase, we will first simply reverse the order of entries in D, that is delta. We loop over the layers and update our weight matrices then, which is gradient descent. We take the dot product of the current layer activation with deltas of the current layer and multiply them with the learning rate. This value is then added to the weight matrix for the current layer. We then repeat this process for all the layers in the network. After performing this weight update phase, backpropagation is completed. After this, we can train our network on any given data set and then make predictions on the testing data set. That's all. Thank you.